The subject of this video is drop impact dynamics. So to begin, we're going to start by asking the question, what is drop impact dynamics? We're then going to move on to the equations governing it, followed by the variations in impact, liquid on solid impact, liquid on liquid impact, some interesting examples, some industrial applications, and then finally the conclusions. So what is drop impact dynamics? When a liquid droplet collides with either a solid or liquid surface, a number of outcomes can happen, such as splashing or spreading. There are two main categories of factors which affect the outcome. These include the droplet, as well as the surface on which the droplet impacts. Within the droplet category, there are a number of different factors including velocity, as well as the angle of impact. The roughness of the surface, its temperature, as well as other properties can also have an influence.
The governing equations of drop impact dynamics can be seen here. These equations can be used to simulate drop impact outcomes for various conditions. The first equation that is going to be discussed is the Reynolds number. The Reynolds number is defined as the ratio of inertial forces to viscous forces and is used to characterize different flow regimes. Laminar flow occurs at low Reynolds numbers where the viscous forces are dominant, while at higher Reynolds numbers the flow is turbulent and inertial forces are dominant. The Weber number relates inertial forces to surface tension. It is often used to analyze fluid flows. A critical Weber number is often reported when splashing begins. The Bond number relates gravitational forces to surface tension. A high value indicates that the system is relatively unaffected by surface tension, while a low value suggests that surface tension dominates. The Froude number is defined as the ratio between flow inertia and the external field, which in this case is gravity. It is sometimes deemed unsuitable for theoretical fluid dynamics, but does however have beneficial naval applications, such as determining the resistance of a partially submerged object moving through water. There are numerous possible characteristics for both the droplet and the surface that can affect the result of drop impact dynamics. For example, before contact, the liquid droplet can possess many properties such as a deformed shape or internal circulation, and can also come into contact with the surface at a number of different angles which affect the outcome of the impact. Due to the number of different conditions that are possible, it was decided that it would be best to focus on spherical droplets and normal impact angles. The surface that the droplet collides with also plays an important role in how the drop behaves after contact. From the diagram, it can be seen that the conditions of both liquid and solid surfaces vary considerably, so it was therefore only possible to discuss drop impact for flat liquid surfaces and plain solid surfaces.
We will now move on to a drop impacting a solid surface. When a drop impacts a solid surface, there is a rapid increase in pressure, which is highest at the contact edge and lowest at the center of the drop. During the initial stage of impact, the drop is merely deformed and compressed at its base. Compressibility of the liquid plays an important role in the initial phase of the impact. The drop can bounce, spread, or splash. For spreading, it usually occurs at low velocities, resulting in a formation of a thin liquid disc called a lamella. First, the lamella expands very quickly and reaches maximum radius within a very short time. It then shrinks to a small size as a result of the kinetic and surface energy of the drop, and is dissipated by viscous processes and transformed to additional surface energy. In the case of a drop which is carefully placed on a surface, the process of spreading is dominated by intermolecular forces rather than the kinetic energy and surface energy of the drop. At higher impact velocities, a jetting motion leads to disintegration of the liquid and splashing occurs, whereby the drop disintegrates into two or more secondary droplets. Again, the kinetic energy and surface tension of the drop plays an important role in the splashing threshold, which describes the transition from spreading to splashing. Splashing occurs at higher Weber numbers, and a critical Weber number is often reported when splashing begins. Bouncing can occur on hydrophobic surfaces, where the surface chemistry means the surface tension is low. A high contact angle causes the drop to bounce. For the case of liquid impact on liquid surfaces, both similar and different outcomes can occur to that of a solid surface. The collision may result in bouncing, coalescence, or splashing. After impact, the drop can float on the surface before eventually disappearing. This is affected by both the cleanliness or purity of the liquid. With coalescence, a small crater is formed, but otherwise the impacted surface is hardly disturbed. The event is usually connected with the formation of a vortex ring below the surface. Coalescence depends on a number of factors, including the impact angle, velocity, and the Weber number. It also requires the layer of gas between the drop and surface to rupture, an outcome primarily influenced by gas density. Both bouncing and coalescence only occur at low Weber numbers. For splashing, the liquid surface is greatly disturbed. It is determined by a critical Weber number, and a characteristic liquid column above the surface indicates splashing has occurred.
Here we are going to discuss some interesting examples of drop impact dynamics that we found during our research. The Leidenfrost effect occurs when the impact surface is very hot, usually between 180 and 200 degrees. This intense heat causes the bottom of the water droplet to evaporate, resulting in a constant flow of steam from underneath the droplet. This thermally insulates the rest of the liquid from the hot surface beneath, as well as causing the droplet to glide easily across the heated surface as shown in the video. This video shows the result when a water droplet impacts a granular surface, in this case sand. The size of the crater is dependent on the size and velocity of the droplet. The lotus leaf shown in this video is an excellent example of a naturally occurring hydrophobic surface. The hydrophobic surface of the plant helps keep it clean and prevent the growth of unwanted organisms on its leaves.
Droplet impacts have proved an important issue within many industrial situations, including engineering. Inkjet printers deliver a very small volume of liquid with extremely high positional accuracy at high speeds and low cost. The pressure of the droplets of ink, along with the angle each droplet is delivered, ensures the minimum amount of ink is used to maximize efficiency. Aerosol droplets. Aerosol is a collection of small liquid particles that are suspended in a gas. Spray angles determine how the particles stick to the skin when using deodorant. It is preferred to have very small droplets that will disperse fully before falling down by gravity forces. A finer mist of aerosol sprays allows the droplet particles to stay in the air longer, and the particles are more easily absorbed. Combustion chamber. Pipe walls modify the size of the droplets and affect the combustion processes. The size of the droplets impact fuel burning along with the angle they are sprayed into the combustion chamber. If the droplets are sprayed on top of the piston inside the engine, it can lead to excessive smoke and incomplete combustion. Crime scenes. Blood spatter analysis. Blood spatter analysts use the formation of blood droplets to accurately reverse engineer crime scenes in order to solve crimes. The distance from the blood source to target can be calculated. The direction of impact can be understood by the angle of droplet impact and how it reacts against different surfaces. Probably one of the most relevant engineering applications of drop impact dynamics is when studying the icing on an aircraft wing. Aircraft during flight have to wrestle with various flight conditions which depend on humidity, temperature and pressure. As aircrafts fly through clouds of supercooled water droplets, the areas around the nose, the leading edges of the wings and the engine cones experience low airflow. This enables water droplets to form on the aircraft to create an icy layer. So to conclude, drop impact dynamics is affected by a bunch of different factors. The equations that govern drop impact dynamics are vital in the prediction and simulation of drop impact situations. There are many various droplet and surface conditions that can alter the outcome of the overall impact. The collision of a drop with a liquid surface initially results with the drop floating on the surface for a short period of time, after which one of three results, bouncing, coalescence or splashing, occurs. This is influenced greatly by the Weber number as well as the impact velocity. Understanding is key when applying drop impact dynamics to industrial processes. especially on wings. Without a deep understanding of drop impact dynamics, aircraft safety would be considerably less reliable. Overall, the phenomenon that is drop impact dynamics plays a larger role in everyday life than many would believe. Understanding and manipulating droplet impacts greatly benefit people, businesses, and safety.